Okay, hello everyone, it's Salar, and this is part 20 of our tutorial to writing a real-time operating system. But after starting to talk about assembly programming from previous part, in this part I want to start talking about memory and main memory, okay, and some instruction about to access to our memory. As I said in previous part, we can keep our value in registers in assembly programming, but in another way we can keep our value in memory, okay, in memory when we want to program a code with assembly language. Okay, let's do open journal, and in this part I want to start talking about main memory. And in most of computer you set that RAM, okay, RAM or main memory. But in main memory we have two distinct categories of memory, okay, two distinct categories. One of that is volatile memory, okay, one of that is volatile memory. What's a volatile memory? Volatile memory is a type of memories, and when you cut off power from your memory, when you cut off power and electricity from your memory, your data will be removed, okay, data will be removed, like RAM in your computer, okay, like RAM in your computer. And we have some types of volatile memory. For example, we have SRAMs, we have DRAMs, and we have SDRAMs. SDRAMs like SDR, SDRAM, DDR, SDRAM, DDR2, DDR3, and until now DDR5. Okay, these types of memory are volatile memory. Okay, and with volatile memory you can save data just when you have power and electricity on your chip. Okay, when you cut off power, your data will be removed. And in the other hand, we have another type of memories, and non-volatile. Okay, non-volatile. Like before, as the name implies, they are non-volatile memory, and you can keep data even after power off. Okay, like EPROM, E2PROM, or now flash memory or magnetic disks. Okay, these types of memory can keep data even after power off. Okay, so with respect to power, volatile memories are temporarily memories, and non-volatile memory are permanently memories. Okay, with respect to cutting off the power of memory. Okay, in each MCU, microcontroller unit, you have memory. Okay, in each MCU microcontroller you have some parts of on-chip memories. You have non-volatile memories and volatile memories, both. Okay, for example, in microcontroller you have non-volatile memories like flash. Okay, you have on-chip flash. And what's the usage of flash? Flash is for keeping permanently data. Okay, for example, your program, okay, your program codes. When you flash your memory, your microcontroller, your MCU, you write your code in flash, okay, in on-chip flash of your microcontroller. And another usage of flash is for keeping constant values, okay, or immediate values. Constant values, like for example, assume that you define and declare a variable, for example, a equal to 100. You should keep this value, this constant value and immediate, in flash, okay? Or for example, assume that you want to write hello world in output. You should keep this constant value in flash, okay? But in all of MCUs, you have an on-chip volatile memory, for example, like SRAM in many of microcontrollers, okay, in many of MCUs. And the usage of SRAM is for keeping variables, keeping stack and heap, or an important part of MCUs, prepheral registers. Your prepheral registers are volatile memories and are SRAMs, okay? So you have non-volatile memory and volatile memory on your microcontroller, and you have flash and SRAM on your chip, okay? You can add off-chip and external memories to your board, okay? For example, you can add SDRAM to increase the memory of your microcontroller, okay, for your variables, stacks, heap, and other usage. Or for example, you can add some off-chip and external flash memories on your chip, on your board, okay? So we have on-chip and off, we can have on-chip and off-chip, volatile and unvolatile on our boards, okay? But what's the structure of main memory, okay? What's the structure of main memory? Let's talk about structure of main memory, okay? I want to talk about a structure of main memory. Let's give you a schematic, okay? Here I have a 4-byte RAM, okay? I have a 4-byte. Let's add it to my notes, okay? Add it to my notes. Desktop 4-byte RAM open, okay? Now here I have a 4-byte RAM, but what's the structure of a 4-byte RAM? A simple 4-byte RAM. You can search for structure of memory, structure of RAM in Google, for example, structure of RAM, okay? And as you can see in this schematic, we have more signals, okay? We have more signals for a RAM. But in this schematic, I just bring some simple structure, okay? Because I want to about the main structure of memory, okay? And you can have some other signals, for example, read, write, enable, and splitted input and output, okay? But it's a simple schematic. But as you can see, I have two bits of address and 8 bits of data. Okay, 8 bits of data means 1 byte. Okay, 8 bits, 1 byte. As you can see, I have 4 bytes. I have 4 bytes in my memory. Okay, so my memory is 4 byte RAM, and I have 2 bits of address and a decoder, 2 by 4. Okay, so assume that A1 and A0 equal to 0 and 0. So I have 0 and 0 here. So the line, this line is 1 and other lines are 0. So this byte has been activated. Okay, this byte has been activated. So I have byte 0 in output. Okay, or assume that put value of 1 0 in A1 and A0. So if you put 0 and 1, now here is 0, here is 0, here is 1, and here is 0, and you can access to byte number 2. Okay, so with 2 bits, so with 2 bits I can have access to 4 bytes, or with 8 bit you can have access to 256 bytes. Okay, or for example, with 32 bits you can have access to 4 gigabytes of memory. Okay, with increasing address bus you can increase the volume of your main memory. Okay, here is a simple structure of main memory. Okay, but in this time I want to talk about ARM computer architecture. Okay, ARM computer architecture. In ARM version 7 for Cortex M. Okay, for Cortex M, the address bus width is 32 bits, so you can have access to 4 gigabytes. Okay, but access to 4 gigabytes doesn't mean that you have implemented all of 4 gigabytes on your chip. Okay, you can have access to 4 gigabytes, but you can implement some parts. Okay, some parts. For example, in my microcontroller, microcontroller STM32F746NG. Okay, here is my microcontroller. If you refer to reference manual, I have a flash, on-chip flash on my microcontroller, and the size of on-chip flash in this microcontroller is 1 megabyte. Okay, 1 megabyte. The start address of this on-chip flash is 0x0800 and 0000. Okay, a 32-bit number, because my address bus is 32-bit, and the end of this part is 0x08 0 f f f f Okay, 1 megabyte of flash memory. Let's open the reference manual of my microcontroller. Search for memory map, and in memory map, as you can see, I can have access to my on-chip flash memory with AXI bus, okay, with AXI bus from this 32-bit address to this address. Okay, 1 megabyte of flash, but I can access to my flash with another bus, TCM bus. Okay, but now I don't want to talk about TCM buses. Okay, you can have TCM bus for your flash and for your SRAM. Okay, TCM for SRAM, TCM for flash. But I don't want to talk about TCM in this time. So with AXI bus, a type of AMBA bus, you can access to your flash from this address, a 32-bit address, to this address. Or for your SRAM, we have 3 types of SRAM, okay, from the 32-bit address to this address. Okay, another time for, it's a non-volatile, for keeping your code and your constant and other things that you want to keep permanently. Okay, and another type, volatile memory and SRAM, on-chip SRAM, 320 kilobytes of SRAM. I have 320 kilobytes of on-chip SRAM on my microcontroller, and the start address is here, and the end of this part is 2004 FFFF. Okay, or another important part of my microcontroller, prepheral register memories. Okay, for example, if you want to configure your prepheral, you need to write some value in some registers. Okay, these registers, prepheral registers, is another type of memory in my microcontroller. Okay, and other microcontrollers. Okay, and for prepheral, the start address of the prepheral in Cortex M7 and Cortex, I think Cortex M, is 40000000. And with respect to your chip peripherals, you have a size for this part. Okay, start address and end address for peripherals. Okay, as you can see, the peripheral start is here. Okay, the peripheral start is here. Okay, and from this address space, you can access to your peripheral registers. Okay, in your main memory. And as you can see, all of addresses are 32 bits. Okay, and for another type of microcontrollers, for example, a microcontroller from NXP, you can go to, let's close that. You can search for memory map, and here, as you can see, the start of memory map is from 0000, 32-bit address, and some of your flash in NXP microcontroller 1064 IMX RT 1064 is here. For example, an ITCM flash from this address to this address. Another part of flash is from here to here, and another part of flash from here to here. In this microcontroller, you have 2 megabytes of flash, or this part from 20000000 to this address is for your SRAM, okay, or other parts for your prepherals, okay, other parts in your address space for your prepherals. And you can have some address space for external memory, okay. You can have some address space to add external memory on your microcontroller. As I said, with 32 bits address bus and address space, you can have access to 4 gigabytes, but it does not mean that all of 4 gigabytes are implemented, okay. For example, here a little part of my address bus is implemented, 1 megabyte, 320 kilobytes, not 4 gigabyte, okay. So if you want to write and read to memory, okay, for example, assume that you want to write to your memory, the store, okay, store or write in ARM architecture means you want to write a value to memory, write a value to memory from register. So you can write the value of your register to your memory, or load or read. You can read from your memory and write it to one of your registers, okay. So we can store and load, store from store to memory and load from memory. As I said in the structure of memory, the structure of memory is set of some bytes, okay. Memory set of some bytes. You can have access to your memory, okay, in bytes, okay, 1 byte, half word means 2 bytes, or word, or 4 bytes. You can have access to your memory with size of byte, half word, and word, and double word, okay, but I will talk about double word, because if you want to write or read double word to or from your memory, you can observe alignment, okay. Observed alignment is so important for double word, okay, or double word, 8 bytes, okay. But before to talking about store and load instructions, first you should pay attention to an important things in memory, and it's known as memory endian, okay. Memory endian, and I want to talk about memory endian. Let's do bring an schematic endian, okay. So what's endian? What's endian in memory? We have 2 types of memory endian in all of architectures. big endian and little endian. And what's big and little endian? First, little endian, LE, okay? Little endian. It means that if you want to write a value from a register, okay? From a register to memory, okay? Here is memory and here is the register. If you want to have value from your register to your memory, for example, assume that I have this value in my register 1 2 3 4 5 6 7 8 7 8, okay? Here is a hexadecimal value 1 2 3 4 5 6 7 8, 32-bit value, and I want to write this value to memory, okay? I have two options in architectures, okay? One is little endian. With little endian means write the least significant byte of register to least significant byte of memory, okay? Reg mem, or conversely from memory to register. From register to memory is write, or store from memory to register is load or read, okay? If you want to use little endian, you should write the least significant byte to least significant byte, okay? And so on. 34, and most significant byte to most significant byte. Another option is big endian, okay? Big endian. If you want to use this option, you should write the least significant byte of your register to most significant byte of your memory, okay? To most significant byte, okay? And if you want to write a value from your memory to your register, this is a full duplex from register to memory or memory to register, okay? You should write the most significant byte of your register to least significant byte, and so on. And least significant byte of your register to most significant byte of your memory, okay? This is known as little endian and big endian in memory. But in ARM architecture and for Cortex-M microcontrollers, okay? As an architecture view, you can have big endian and little endian both for your SoC, for your microcontroller, but almost all of microcontrollers in Cortex-M implemented as a little endian, okay? Cortex-M is a little endian. And I've never seen a big endian Cortex-M microcontroller, Cortex-M microcontroller in market, okay? Almost, I think all of Cortex-M microcontrollers are little endian. What means little endian? Least significant to least significant, from register to memory or memory to register, okay? If you want to transfer a byte or half word, if you want to write a half word to register, for example, assume that you want to just write this part, okay? List to list, or for example, for big endian, must to must. But in Cortex-M are little endian, okay? And you can't change this option, okay? It's unchangeable in Cortex-M microcontroller, and you can change the access of your register to memory or memory to your register, and you can't change this access to big endian. Okay, it's implemented on silicon. Okay, and you can't change that. It's unchangeable. But let's start talking about instruction of access to memory. Okay, first I want to talk about a store. Okay, what's a store? Right, from register to memory. From register to memory. How can I write a value from register to an address in my memory? The instruction is str or store. RT and RN. What's RT and RN? With str and this instruction, you can write the value of RT to the address which is saved in Rn. Okay, you can write the value of RT to address, to this address. The address is saved in register Rn. Okay, we have some other types of str instruction and known as offset addressing, and one of those is immediate offset. Okay, what's the instruction? Another time, str from this register to address of this register plus an offset. Okay, an immediate value, that is address. So you can write the value of RT to this address Rn plus immediate. Okay, the range of immediate is from -255 to 4095. Okay, this range is not a symmetric range because of different encoding in ARM. Okay, and it's a asymmetric range from -255 to 4095. Okay, it's an asymmetric range because of different encoding in ARM architecture. And there is another of offset addressing and known as register offsetting. Okay, here is immediate offset. We have another type of store in memory, and the instruction is str another time from RT to address of Rn plus the offset that's saved in another register. Okay, so from RT to address of Rn plus Rm. As the value of Rm is 32-bit, you will have much more bigger range than this little range. Okay, you have your range here is 4 GB. Okay, your range here from your range here from -231 to I think to 31 minus 1. Okay, here is the range. But as you can see, because of the 32-bit register, you can have tooth complement negative value. For example, offset -4 in this way is 0x f f f f and f f f c. Okay, for negative offsetting you should create tooth complement value, okay, in this way, and it means -4, okay, for us. But here is range. Okay, the range in offset, register offset is so big. Okay, and with this offset you can have access to all of your memory address. Okay, so let's give to you some samples. Okay, first let's open Eclipse. Okay, here I'm in Eclipse and I have a main.s, an assembly file, and here I want to talk about a store instruction. Okay, so first let's build my project and start debugging. Okay, here I'm in debugging perspective and I'm in the first line of my code, my main.s file. Okay, and here in this tab register I can see all of my register. So how can I see and inspect and have access to memory? To have access to your memory, go to Windows tab, in show view, open memory. Okay, memory viewer. Okay, open that, and here in this tab, okay, here is memory tab. Okay, and in this tab you can have access to your memory. For example, assume that I want to see a part of my memory. Before that, right click on this page. Okay, before that, right click on this page. Before that, click on this plus and add an address. For example, 0x20000000. Okay, the start of my sram. Okay, I want to write some value in this address and inspect this address. A startup SRAM, a volatile RAM in my microcontroller. Okay, because I want to write some temporary value from register to my memory, I can use SRAM. Okay, from this address. Another 0. Okay, a 32-bit value, a start address of my SRAM. Okay, here, if you want to see this format, right click on this page, go to format and set the row size to 1 and column size to 1 and set as default, and okay, now here in my SRAM address, here is byte 0, byte 1, byte 2, byte 3, and so on. Okay, here is a part of my SRAM and I can inspect this part. Okay, so assume that I want to write this value 1 2 3 4 in upper part of register 0 and 5 6 7 8 in lower part of register 0. I want to write this value 1 2 3 4 5 6 7 8 from register 1 to my SRAM. Okay, so put this value to R1 and put your address to register put this value to R0 and put your address a start of your SRAM. Okay, here is a start of my SRAM to register R1. Okay, and with this instruction str, you can write the value of R0 here 1 2 3 4 5 6 7 8 to the address that saved in R1 to this address. Okay, so I want to write this value to this address, and my memory is my architecture and my core is little endian. Okay, has little endian access to memory. So let's run to store. Okay, now as you can see in register, the value of R0 is 1 2 3 4 5 6 7 8, and the value of R1 is an address, a start address of my main memory. As you can see in memory tab, here I have 0 0 0 0 in my main memory. If I run next command and run this store instruction, I will write this value to this address. Let's do run. Press F6 to step over, or here is next. Okay, here as you can see I have this value in my memory. Okay, the least significant byte 782 least significant byte of memory. Okay, least significant byte to least significant byte, and most significant byte of register 1 2 in 3. Okay, most significant byte. Here is an little endian access to memory. Okay, another time I want to talk about immediate offset. Okay, as you can see, another time the value of R1 is this address, and the value of R0 is this value, and I want to add my address with 4. And this time I want to write this address, the value of R1 plus this immediate offset. Let's run this instruction. So I should write in this part 4 5 6 7 because I want to transport a 32-bit and 4-byte value. Okay, another time run next, another time in 4 5 6 7 8, like here. Okay, a little endian access, least significant byte to least significant byte, and most to most. Okay, so another time I want to use register offsetting instruction. Okay, this instruction transport the value of 8 to register R2. Okay, and run this instruction. So the value of R0 is start of my SRAM and offset is 8, so I can write in this address. Okay, let's run this instruction and run store. Another time in this address. Okay, 8 9 10 and 11, A and B in hexadecimal. Another time 78 56 34 and 1 2. Okay, a little endian access. Now assume that I want to use register offsetting but with a negative value, negative value with tooth complement values. Okay, assume that I want to write to this value. Okay, here is 12. C means 12. Here is the base address 2000010 minus 4. Okay, here is 16 minus 4 is 12 and means C. Okay, but minus 4 here is a 2's complement value. Okay, this is the base, this address is base, and here is offset, a negative offset. So let's do first write this address to register R1, okay, with these two instructions, move W and move T, and change the value of R1. Run next, another time run next. As you can see, the value of R1 is this address, and minus 4 is 2 and C, okay, and minus 4 is here. Okay, another time let's do load the value of R3 with this value, 2's complement of minus 4. So the value of R3 is minus 4, and the hexadecimal 4 is here. Okay, 2's complement number. So I want to write another time the value of R0, 1, 2, 3, 4, 5, 6, 7, 8 to this address, but with register offsetting and a negative value. So let's do run that. So go to memory. As you can see in this part, C, D, E, F, I have another time the value of R0. Okay, the value of R0. So how can I write a byte value or half word value in my main memory, okay, with a store instruction? Or how can I have unaligned memory access? What's unaligned? As you saw, all of my address was divisible by 4. For example, 08 2000008 here is divisible by 4. So what's about if I want to write this address 1, 1? It's not divisible by 4. Okay, it's unaligned word access. Okay, a word aligned access address is an address that is divisible by 4, or a half word for word access. An aligned address is divisible by 4 for half word access, and half word aligned access is divisible by 2, and for byte access you can have access to all of your memory addresses. Okay, but what happens, for example, if I want to write a value, a word in this address, a word 32-bit value in this address? Okay, in the pre-config and preset configuration in almost all of microcontroller, you can have access with unaligned addresses. Okay, but you can change the configuration of your microcontroller and forbid the unaligned access. Okay, alignment and unalignment address are loaded by your microcontroller but are configurable. Okay, and you can change this configuration, and you should study about that by yourself. Okay, study about alignment access and configurations. okay, for your microcontroller. It's your homework. Okay, I don't want to talk about that more, but I'll give you some examples for unalignment access. Okay, but configuration to change this permission comes in ARM version 7 architecture reference manual, and you can study about that. Okay, so another thing is writing byte and half-word values in memory. If you want to write a byte value in memory, you should use strb instruction instead of str. With this instruction, you can have byte access to your memory, or for half-word, you can use str and h. All other options is just like str. Okay, for example, immediate address offsetting, register offsetting, and other things. Okay, another accessing is double word. You can use strd, and for your register value you have rt and rd, for example. Okay, and you can write the address like other instructions, rn with an offset. Okay, but immediate offsetting in double word access is from this value to this value. Okay, for immediate offset. Okay, you should study about double word access to memory in architecture reference manual. The instruction is here. Okay, but let's give you some other examples. As you can see in this line 27, I want to write a value in unaligned address. The value of R1 is here, and I want to write in this address. Okay, in this address 20000011. It's not a word aligned address. Let's run this instruction. As you can see, I can write to this unaligned address. Okay, let's add another address. Okay, I've added another address here. Okay, you can write in unaligned address. Okay, it's an unaligned word access. Okay, so how can I write a half word in my main memory with strh half word? Okay, and you can write your half word in unaligned address. Okay, the value of r0 plus 7 is unaligned access for half word access. Okay, and in this time I want to write in this value. Okay, so before to run sorry, in this instruction I want to write a byte value in this address. Okay, r1 plus 5. Here is next instruction. I want to write the value of r0 to this address, r1 plus 5. But the value of r0 is 32-bit, but I want to transport just 1 byte. Okay, which byte of this which byte of this value will be transported. Here it's 32-bit value, but I just want to write a byte of 1 byte of this number. Which byte will be transported? Let's do run instruction strb. Okay, write a byte from this register to this address r1 plus 5. Run that. As you can see, in this address 78 has been transported. Okay, least significant value of register. With strb you can transport the least significant byte in your register. Okay, and another time run this instruction r1 plus 7 and on alignment access for half word in 2 and 17 in hexadecimal. 2 lower bytes have been transported. 2 lower bytes have been transported. So with byte and half word access you can transport the least significant byte and least significant of half word, first 16 bits in your register. Okay, lower part of R0. Okay, this was about a store instruction, write to memory. But what about read from memory or load instruction? The instruction is LDR, and other options are completely like str. Okay, for example, you can write a value with an offset to register RD, in this time from your memory. For example, for register addressing, from this address to this address. For read from an address in your memory, you can have byte access, half word access, double word access, word access, and other things are completely similar to str. Okay, are completely like store instruction. Okay, all of offset, all of alignment are completely similar to a store instruction. Okay, and you can study about that, but I can give you an example. In this time I want to load half word value from this address r1 plus 7 to register r4. The value of r1 here is 20000010 here, plus 7 is here. Okay, I want to write this half word 7 and 8 to register r4. Okay, read from memory. As you can see, the value of register r4 is 0, and if I run this instruction, now the value of register r4 is this half word 5678 in little endian. From this address 7 and 8 to register r4. Okay, the value of register r4 is loaded, has been loaded from memory. Okay, so with a store and load instruction you can write to memory and read from memory, and all of options are similar. But we have some other types of load and store from memory that known as pre-indexed and post-indexed access. Okay, but I will talk about them in future parts. Okay, for this part is enough, and thank you so very much to see me, and see you soon in the next part. Thank you very much.